Okay, so the question was, where can you find the objectives for the final exam? Hold on, we gotta do our cute little security thing that we do here now. Okay, so if you go to Canvas, so here's your Canvas course, and you go to modules, this is where you find most of the information. I don't know if you guys have picked up on this. I always just go straight to modules. But here's all the information that you're going to find and that you need for the different modules. Here's where I'm posting the current recordings. So I don't know if you've been listening to the old ones or the current ones. It doesn't matter to me. But this is where you'll find the newest ones. But then if you scroll all the way to the bottom, what you're going to find is final exam objectives. This is the thing, and I think I may have mentioned it the first day or two, but what I would be doing if I were you is now that we've finished up a module, I'd come into here and I'd probably go, if you have the course packet, the loose leaf version, if you didn't get it bound, I would pull out objective 5, 8, 9, 10, 11, those ones, and put them in a separate binder. And that binder would say final exam. And then I would study those for a little bit, go on with module 2. Be kind of doing my module 2 thing. Finish module 2, go back to your final exam binder, study module 1 again. Just these guys, because they're the ones that are going to pop up on your final. Pull out the ones from module 2, put them in there. So now you've got module 2 objectives, and you're studying those guys. Does that make sense? So that when it comes time to do the final, you've been looking at this stuff all semester long and remembering it, and you don't have to try to relearn it. Okay, I think I told you before, the final exam average is like a 75%. I don't like seeing that, and I don't know how to motivate you more to get going on this guy before finals week. Okay, and you'll notice, though, that it's not every single exam or every single objective. So the other thing that you could be doing is as you're starting this module, run through here and highlight these objectives in the module that you're studying. So when you go through, you're like, oh, this is one of those objectives that's going to be on my final. Probably better have this guy wrapped up pretty good. Okay? So thank you for asking. It's a really good thing to be doing now so that when it comes time to do the final, and we've gone through 10 modules worth of stuff, you're not like, oh, yeah, I think we talked about chemistry 9 years ago. All right. Other questions, concerns? Okay, let's have a moment of honesty, shall we? How many of you guys hate chemistry? Wow. It's like all of you. Awesome. Me too. Me too. Me too. So my father was a very smart individual, I believe. He and other people that know him say that chemistry kept him out of medical school. So he was a jeweler growing up, so it was a little bit not as easy as it may have been had he been a physician. But yeah, chemistry is just one of those things that it just seems to not click with a lot of people. So the fact that we're going to cover chemistry for a couple of modules tends to freak people out. So what I would like you to do is take all of those preconceived feelings that you have about chemistry and try to just dump them. Get rid of them. Let's all go into this fresh and say, hey, new start, new approach, new teacher. Let's at least give it a shot. Because if you walk into this being like, chemistry sucks and it's stupid and I'm never going to learn it, then you're already kind of toast, right? But I promise we're going to take this slow enough that you'll get it. Okay, and that's a problem for 2 reasons. Number one, it's slow. So some of you are going to be like, oh my gosh, I get it. A proton's positively charged. Shut up. And if you've already had chemistry, and especially if you've done well in chemistry, you're going to hate the next couple weeks. Okay, you can just go take a break if you want. Don't, because then you'll fail. But I don't know how to start from the ground up and keep it simple without boring the crap out of some of you. So if you're bored, I apologize. Just take a nap, right? But we're going to start very, very basic ideas here. Okay, and I'm going to go a little bit different order than what you have in your course packet. So if you want to get out just a plain piece of paper, it's probably not a bad idea here for us to just jam a little bit. So the idea is if I'm going to start talking about an organism, that I've got to kind of break that organism down into different systems. And if I'm going to talk about a system like the respiratory system, I can't really just jump right in and start talking about the respiratory system without a basic understanding of what the tissues of the respiratory system do. And I can't really talk about tissues unless I've talked about cells. And I can't really talk about cells unless we talk about how cells function and what's going on in the cell and the parts of the cell. And that doesn't really make much sense unless we start talking about what's moving in and out of the cell and how the cell makes energy and how the cell builds proteins. And that doesn't make sense unless you know what proteins are and ions are. And you get my point? So we got to start at like the ground level, or what we consider the molecular level. And then we'll build up from there. Okay, so molecular, or the atomic level, we're talking about how small we can get if we're talking about different things in nature. So I can take this table and start breaking it down into tinier pieces, little chunks of wood. And then I can zoom in on those chunks of wood and find out, okay, what made that wood? Okay, there's probably plant cells in there. And I can zoom in and zoom in and zoom in. The idea that I want you to kind of grasp right off the bat, the smallest I can get, and we're not going to get all theoretical and get weird into physics, but the smallest particle in the world that has like actual describable qualities, we call an atom. Okay, that's it. You can't break that guy down any smaller. Then you start getting really weird, like I said, theoretical stuff. So we're going to spend some time talking about what an atom is. But the thing to know, these atoms are made up of three pieces: protons, electrons, and neutrons. Okay. It's as small as we can get. If you're like, well, what if I broke down an electron? This is the answer I'm going to give you. I don't know. Nobody knows. Well, I think actually people do know. Shut up. I don't care. Okay? For us, this is as simple as it gets. You can't break those guys down any smaller. Okay? A neutron isn't made of like tiny other little pieces that we put together. This is as small as we can get. Okay, each of these particles has some properties to them so that when they come together, they function as a whole. These are easy, and we're going to keep them easy. Again, none of this theoretical crap. We're just going to keep it nice and pretty and simple. Okay, we'll start with the proton. Things you need to know about this guy. You need to know about all of these particles, the charge of it, where we would find it in our atom, and how much does it weigh. Okay, that's what you need to know. I'm going to keep it really simple. So protons, they are positively charged. Okay, you've played with charges before, like with a magnet. If you've ever remember back in elementary school, and you had the little bars that were magnets, and one end was positive and one end was negative, and you'd push them together, and it was fun. And same idea. That's what we mean by a charge. Okay. The protons we find in the nucleus of our atom, and we'll show you what that looks like in a second. And here's the weight, 1. Don't ask me units, don't ask me 1 what, just go with 1, because we're keeping it simple. It weighs 1. Okay, the neutron, for its charge, what would you guess? Nothing, no charge. It's neutral. Okay, so if you're talking about something political, you might find people on two ends of that political scale. I love Donald Trump. I hate Donald Trump. You may find, and maybe that's a bad example because you probably won't find, but you may find somebody who's neutral, who's like, who's Donald Trump? We have a president? I don't really care about that stuff, right? They're kind of not on one of the sides. That's what we would consider a neutron, no charge. Okay, where do we find this guy? We find it in the nucleus. The nucleus, we'll see, is kind of in the middle. And we're going to say that this guy weighs 1. Same weight as proton. Okay? Have we blown any minds yet? No one's going to drop the class at this point. Okay. Electrons. These guys are negatively charged. They're outside of the nucleus. And they weigh Nothing. Don't raise your hand and be like, how can something weigh nothing? Go with it, okay? We could say it weighs like 0.00000000001, blah. Let's just say 0, because it's easier to work with. Okay? We're still good. I know this is slow and almost like condescending, but I want it to seem very, very simple. So if I had an atom, and this atom was comprised of 1 proton, and that was it, what would be that atom's charge? Positive. What would that atom weigh? 1. Done. Okay, what if that atom had 1 proton and 1 electron? Now what does that atom weigh? Still just 1, right? Because electrons don't weigh anything, right? We're going to consider that 0. But what would be the charge of this guy? 0, no charge, because the proton is positive, the electron is negative. Those guys cancel each other out. Okay? So what if this guy had 1 proton, 1 electron, and 1 neutron? Now it's going to weigh 2, but what's going to be its charge? Still 0 or negative, no charge, because the neutron doesn't contribute anything to the charge. So far, so good. Okay, got some really awesome animations in this presentation. Worked pretty hard. Okay, so there's my nucleus, proton plus the neutron, and the electron. Get ready for this. This is going to blow your mind. It's technology at its finest. The electron, right, super fun, kind of orbits or flies around the outside. So it's not ever going to get stuck on the inside. It just kind of hangs out on the outside. Okay. There it is all written down for you if you care, but we just talked about it. I put them together, and then now this whole thing we would refer to as an atom. Okay? The individual particles are what comprise or make up that atom. So here's an atom. Here's another one. This guy is hydrogen. Okay, and we'll tell you how he came up with this. So hydrogen. This guy is also hydrogen. And I can just use its little symbol. It's easier to write. Still hydrogen. I got a whole lot of hydrogen. All of this together, I don't know why that guy just spins, hydrogen. Okay? It doesn't matter how many individual atoms of the hydrogen I have. If they are all the same, this is hydrogen. Okay? Okay. Now if I start putting them together, and I'm smashing them together, I've changed the atom. Okay, because what hydrogen was, it was 1 proton, 1 neutron, and 1 electron. That's how we defined hydrogen. Once I start messing with these numbers, I'm going to change the way that this thing functions. So now if I'm looking at this, what have I got? I'll even add some charges in here for you to help you out. How many protons do I got? 2 protons. Neutrons? 2 neutrons. Electrons? 2. Anyone know what this is? Good. Yeah, this is helium. Helium's a little bit different than hydrogen, right? You're not going to go to a birthday party, grab a random balloon, and be like, "Ooh, does this have helium or hydrogen in it? I'll just inhale it." Oh, that had hydrogen in it. Uh-oh, right? And you explode. You're probably not going to explode, nor should you be sucking the helium. But the idea is those two gases are very different. We do different things with them because they have different properties. Really, the only thing we changed is the number of these subatomic particles. But by changing those, helium and hydrogen perform very different. They act differently. Okay. What would be the weight of a helium molecule? 4. 2 protons are each 1, 2 neutrons are each 1. What would be the charge of this guy? Neutral. Why would this be neutrally charged? Don't I have a bunch of electrons, a bunch of protons? they balance or cancel each other out. And that's something you got to remember. If I have an electron for every proton, balanced. Cool, easy. It's when those numbers start getting imbalanced, where I have like 5 protons and only 4 electrons, that I would start to see a charge. But as long as I have the same numbers there, we're going to be neutral. Is that okay? Okay. Okay, so what would this guy be? This right here. Hydrogen still, right? Okay, what about now? Oh, I've messed with it a little bit, right? So now I have 1, 2, 3, 4 protons, 1, 2, 3, 4 neutrons, and 4 electrons. Okay, so this guy's going to weigh what? 8. Okay, because of the 4 and the 4. What's going to be its charge? Neutral, because I've got a balance of electrons and protons. Okay, and the only other thing I'm kind of showing you here is that electrons like to hang out in pairs. Please. Not necessarily even, but as long as there's a balance between protons and electrons. So if I had 3 protons, but 3 electrons, I'm still good on charge, neutral. Okay. What if I, tricky question. Did you guys see that? I'll back up so you can see my animation, because I'd hate for you to miss it. Oh no, what have I done? So now I have 4 protons, but what for electrons? 3 electrons. So what would be the overall charge of this guy? Plus 1. Why plus 1? Because I have 1, 2, 3, 4 positively charged protons, but only 3 negatively charged electrons. So 4 positives minus 3 negatives gives me 1 positive, if you want to think of it that way. Okay, it seems like really elementary, kind of childish math. You got to be able to think this way, because we'll give you these situations, and we'll say, hey, what would happen if this molecule lost 2 electrons? You'll be like, well, okay, now it's positive 2. All right. Uh-oh. You guys see that? What'd I lose? A neutron. So what changed? The weight. Did I change the charge? No. All that changes is the weight if I lose a neutron. Beautiful. Okay, here's from your book now. So we'll go back to your book's definitions, because I think looking at it and then adding the words makes a little bit more sense. So we just barely defined this guy. An atom is the smallest unit of matter which are going to have properties. Okay, I can't get any smaller than like a hydrogen or a sodium or lithium. That's one individual atom. Once you get smaller than that, now you just have the subatomic particles. You just got pieces of the thing. Okay, an element then is another way of saying an atom. And we'll see we kind of say the two interchangeably. But you're going to find element, we add the names to these guys much more often. So the element oxygen, the element carbon, the element nitrogen, the element hydrogen. Okay, so the element hydrogen is made up of hydrogen atoms. Okay, if I had a bowl of carbon and I were to take that carbon out and try to get it as small as I could, all I would find is a whole bunch of little carbon atoms. I can't get any smaller than that. Okay. I don't know if it ever helps. So my kids love Dippin' Dots. You guys got Dippin' Dots before? But they never want Dippin' Dots where you can like buy Dippin' Dots normally. They only want them at Lagoon, where they're like $12 for a thing of Dippin' Dots, right? And I'm mean dad, and I never let them have them, and there's much tears and crying. But if you got a cup of vanilla Dippin' Dots, and you were to take a spoonful of it, right? It's going to taste like vanilla. Agreed? Doesn't matter how many of those little dots are in your spoon, it's vanilla ice cream. Well, what if you were to eat them one dot at a time? What would each individual dot taste like? Vanilla, right? That's kind of the idea. So each individual carbon atom has the properties of carbon. If you put billions of them together, it's still going to be carbon. That makes sense? So just like a whole bucket of Dippin' Dots that are vanilla would be vanilla flavored, each little individual guy is still going to be vanilla. Okay? That's kind of what we mean by like atoms and elements. You can have truckloads of elements, but as you start to break them down, you're just going to find individual atoms that behave, that are the same as that truckload of stuff. And that'll make more sense as we kind of move along. These are the 4 basic, most important, most abundant elements that you're going to find in the human body. You need to have a handle on their names, their chemical symbols, and where we find them, or kind of what they're doing. But hopefully you know from being a kid that what's the most abundant thing in your body? Water. We write it as H2O because we've got what? 2 hydrogens and an oxygen together. We're going to talk about that. So it doesn't seem to be very crazy that we would find hydrogens and oxygens on this list of the main chemicals, or the main elements, sorry. Okay, so oxygen, obviously part of water. We're also going to see it in a lot of organic molecules. Hydrogen, same idea, in the water. We're also going to find it playing a role in like pH. So when we talk about the pH of something, that's coming down to these hydrogen ions. And we'll define ion in a second. Carbon's pretty important. This is going to be the backbone or the key feature to all organic molecules. So when they go looking for life on other planets, they always look to see if there's water somewhere there, or if there is evidence of water having been there. And then they look for carbon. Because as we understand it, life can't exist without carbon. Okay, next module, module 3, we will spend so much time talking about carbon, you'll be like, shut up with the carbon. Okay, but that's the idea. You don't have organic or life compounds without carbon. And then nitrogen actually plays a huge role in things like proteins and nucleic acids. So we see quite a bit of that too. So if you look here, of everything in your body, these major elements constitute just about all of you, 95%. The lesser guys play an important role, but we don't see them as abundantly. Okay, so here's the lesser guys. You also need to know these, chemical symbol and what they're doing. But a lot of this you've heard before. Okay, this is basic nutrition stuff. This is stuff you see like on a TV commercial, so this isn't too crazy. So calcium, our little chemical symbol is Ca, and you've heard that calcium is important in bones and teeth. It's true. You got to have calcium to make those bones hard and make those teeth hard. Can you imagine having soft, squishy teeth? Kind of awkward, right? You go to eat something, your teeth just all fall apart. So we need that ion, and we'll talk again ion in a second, to help build those molecules. Okay, it's important for blood clotting. We need it for some hormones. We can't contract muscle without calcium. Okay, phosphorus. We also see this guy in bone and teeth. It's also a critical component of adenosine triphosphate, which is our energy molecule. And we'll get to that eventually too. Potassium. And notice potassium. The name is potassium, but its symbol comes from the Latin term kalium, okay, which is K. So get that in your head right now. Even though it's spelled with a P, its chemical symbol is K. All right, so P goes with phosphorus. So we need this guy. It's a cation, which just means positively charged particle, but we have a lot of it inside the cell. Learn that now and never forget it. Potassium is highest inside the cell. That's going to come up a million more times this semester, a million more times next semester, a million times in patho, and for the rest of your life. Potassium is highest inside of our cells. In fact, we don't really have much of it outside of the cells. It's all inside. Okay, a little bit of sulfur is important for some vitamins and some proteins. Sodium is kind of the same deal with potassium. It comes from the Latin natrium. That's why it gets an Na symbol. But this is the one that we see. Again, cations, positive charge. But this is outside of the cell. So if I ever see you like out on the street, just like on a Saturday, and I recognize you from this class, I'm going to be like, where's sodium? You'd be like, dude, that's a weird question, but where is it? You're like, outside the cell. And then I'll hug you, and no, I'm just kidding. But you got to know sodium's high outside, potassium's high inside the cell. That's critical for how neurons fire. It's critical for how muscles contract. It's critical for like how life occurs. Please. Great question. Extra meaning outside of, and cell. So it's saying the fluid that we would find outside of the cells. So the cells are kind of like floating around in their little fluid. We would expect that fluid to be high in sodium versus the fluid inside of a cell that's going to be higher in potassium. Great question. Please, you guys, stop me if one of these terms doesn't make sense, because I don't want to leave anyone being like, wait, what is that? I don't remember what that is. All right, a couple more. Chlorine. See this guy also playing a role in how water is balanced, and we see this one also extracellularly. It's negatively charged. What would you guess this positively charged sodium and this negatively charged chloride like to do with each other? Like Na and Cl. What do you recognize this to be, anyone? This is just table salt. So these two molecules come together, and we'll talk about why they do down the road a little bit. But we see these guys hanging out. Sodium and chloride are like little buddies. Okay, magnesium, another lesser molecule here that we need for enzyme activity and some chemical reactions. So we'll talk about how enzymes make those chemical reactions go. But a lot of them require magnesium. And then iron, this last one, we see it in the hemoglobin molecule that we see inside red blood cells. So those red blood cells are intended to carry oxygen throughout our body, and they can only do it if there's iron present. So you've got to have some iron. In fact, you've heard of people who are iron deficient. What's the diagnosis we give them? Iron deficiency, anemia, meaning they don't have enough red blood cells. They can't carry oxygen well enough, okay, because they don't have enough iron. Okay, we okay on that? We're not going to make you memorize the periodic table. We're not going to make you memorize how these guys come together. We want you to know, hey, here are the names. Here's a little bit about what it does in the body. Okay, question, then we'll come back. We haven't gotten there yet, so don't stress yet. So ionized, when it talks about like chlorine being in an ionized form, you see it's got a little charge with it. That's what we're referring to. But kind of why would it have a charge? We haven't gotten there quite yet. Yeah, but ion or ionized, we're just talking about a charged particle. But if you're to answer that right now, what would you guess? How would I get an ion instead of just an element? How am I going to end up charged? I've got differing amounts of what? Protons and electrons. Yeah, so how they're different and why they end up different, we'll get to that. But anything that carries a charge doesn't have equal amounts of protons and electrons. That's all we're saying. Oh, good. Okay, cool. Other questions? Okay. So, a couple more definitions. I used the term molecule a second ago. This is probably the one that I'm going to use the most because it seems to fit most often. But what a molecule is, it's just two or more atoms that are joined together. Okay? Don't worry about the terminology. Two or more things stuck together is going to be good enough. Okay, so it could be like two oxygens that have come together, that they're just happier together, so they're just going to hang out as O2, two oxygens. We would call that a molecule of oxygen. Or they can be different atoms, or from different elements, like H2O. So I could consider that a water molecule. If we're using the term compound, then those two things that are hanging out together have to be different elements, like water or calcium chloride or salt, like we were just talking about. They can't be the same. Okay? So all compounds would be molecules. Molecules, just two things stuck together. But the only time a molecule is going to be a compound is when? When it's made of different elements. Okay? So some terms that unfortunately are a little bit confusing there. Okay, some of this, in fact, let me tell you, this module, there's a lot of information we're just kind of throwing at you. Like, hey, here's a little bit of information about stuff. Here's a little bit of information about stuff. And then we'll kind of come back to the elements and how elements come together. Okay, so if it seems like we're bouncing around for a minute, we are. Don't stress out. So solids, liquids, and gases, these are our properties of mass. You don't find mass in a property that's not solid, liquid, or gas. There's this other category called plasma that's kind of some liquidy, some solidy, some. Don't stress about it. We don't find plasma. Crap, now that sounds weird. I was going to say we don't find plasma in the body. When we talk about plasma in the body, we're talking about something totally different. Okay, not like some weird form of mass. So don't stress about that. If you've heard about it, if you've studied it in physics, you probably know more about it than me. Cool. But solids, these guys are the ones that have a definite shape. This table is solid. It has a shape. You are solid. You have a shape. Okay, the particles, the atoms that make up these solids, they're very tightly packed and they're stuck together. Okay, you can compress this if you wanted to, like smash it, but you're not going to be able to smash it very easily. Okay, liquid, these don't have a definite shape. So really, what's the water in your water bottle? Does the water have a shape? Well, it's the bottle that determines the shape, right? The water just conforms to it. So no shape, but it does have a definite volume. You can measure this. The molecules are a little bit more mobile. They're moving around more. They stick to each other, but they're kind of spreading around. And that's why you get that volume or that shape kind of just taking the shape of the container. And they're slightly compressible. Not really. Okay, don't stress out about that. But gas, then, indefinite shape, indefinite volume. Now, I can take it and I can compress it into a volume. You guys have all seen like your propane tank for your barbecue. Okay, that would have a certain volume, and really we would measure it in pressure. But I can take gas molecules and compress them very easily. Okay? Because those individual atoms just kind of bump into each other, but they're not stuck to each other. Okay, gases don't like to stick to each other. Okay on that? Okay, I don't like this idea of potential versus kinetic energy. So I'm going to tell you one of my lifelong dreams here. You guys ever heard of Barbie Jeep racing? Yeah, Barbie Jeep racing, right? So this is what, every time I think of potential and kinetic energy, this is what I think of. Maybe. If YouTube ever wants to pull up. So what these people do, and I shouldn't make fun, but it's kind of a certain type of person. Is redneck politically correct? Is that all right? But what they do, oh, come on, why is this not pulling up? I know, right? Barbie. Maybe I'll just pull up the pictures then if I can't get video to play here. It's like they're blocking YouTube or something from me, which is not cool. But anyway, what you do is you get like those like kid Power Wheel cars, and you run them to the top of a hill, and then you just go down on top of them, like as a full-grown adult on top of this little thing. And you crash and you wipe out, and people die, and everyone's lined up to watch. And so it looks super great. I've never done it. So when I come to class one day with like a broken arm, you're going to be keeping Barbie Jeep racing, right? But it's a very good example of potential versus kinetic energy. And I wanted to show the video. I don't know why our internet's being stupid here. But the videos are funny because they'll sit at the top of this hill, and these hills are like steep. You know, like, and a lot of times these races, they're not like a cute little path. It's like straight downhill. But the idea is, and I'm sure it'll start playing as soon as we keep talking, like an arrow pulled back in a bow and arrow, or what I think of like that Barbie Jeep at the top of a hill. Okay, so here's your little Jeep, and here's you. You're ginormous, right, sitting on this thing. My drawings are awesome. Most likely wearing camo of some sort, you know, a trucker hat probably, really tight. Just kidding. Watch the videos though, you'll be like, okay, that's those people's sport. But right here, if you're not moving, what you have is potential energy. Like if you start going down that hill, now we're going to get a release of energy in the form of movement. Okay, or an arrow pulled back but not released, that's potential energy. Like when your parents tell you you have all this potential, it's kind of like a dig. Have you ever thought about that? They're not being really super nice. They're kind of saying what? Do something with your life. Yeah, move. Go get out of the house and do something, right? You've got so much potential. I mean, you're not... Anyway, potential energy it's there. It just hasn't been released. Kinetic energy is now the energy that we see, and it's usually movement-based. Okay, in fact, anytime you see kinetic or kinesi, this term, I want you to think movement. So once Homeboy starts going down the hill, tons of kinetic energy. Okay, they smash into each other and they roll a million times, and we got some movement, some energy going. Okay? In the body, we have certain molecules that molecule is going to have a lot of potential energy. And then when we do something to it and break it down, now all of a sudden I can get that energy being released. And those molecules are really, really important to us. If we didn't have them, we would die. Okay? We get on two types of energy. Okay, so those reactions, the chemical reactions that take place in the body, they either take the energy and store it, or they take the energy that was stored and release it. Okay? And you guys have seen this. If the energy goes into, we use the funky term endergonic. Okay, but that's what it means, like into, energy is going. So I take the pieces of whatever I'm doing, and I put them together. It takes a little bit of energy, but now what I have is I have stored energy in that product. Okay. I'll be an example of this. You guys remember, and I know it's going to be hard to believe, I was kind of a nerd growing up, but we used to take popsicle sticks, you remember, and you'd like bend them into like these like crazy contraptions, but there would be like so much like twisting and bending of those popsicle sticks that when you threw them, they'd like explode. It was so funny. I didn't know. Little paper clip. Remember like bending the paper clip into a triangle? You put the two ends together so it's sitting there. Or a mouse trap. I have mouse traps. Do not make me go get my mouse traps. But you pull the mouse trap back and you set the little lever, right? You're putting energy into that thing and you're storing the energy. And then it takes a little bit of what we call activation energy, like touching that mousetrap, and what? We get that energy coming out. So if I'm winding up the mousetrap, we would consider that like endergonic. If I'm touching it and releasing it, then I get exergonic. Just because I'm on a kick and the internet's, oh, it's not going to work, is it? Have you guys seen Mousetrap Roulette? It's so not going to work, is it? Okay, we got to get our internet figured out. How am I going to survive without being able to show you dorky YouTube videos? But basically, people like, you get mousetraps on a wheel and you put it behind a box, and then you spin the wheel and you just stick your hand through and hit it. It's way better than roulette with like a gun, right? But you touch that mousetrap, it snaps on your finger. A lot of energy coming out, a lot of pain involved. People do it with their tongues too. Seen that? Yeah. So if you're looking for something fun to do and you're crazy drunk, consider mousetrap roulette. But the idea is you got reactions that take the energy and store it. Sometimes we call that type of reaction anabolism. Okay? Dudes at the gym who are taking anabolic steroids, what are they trying to do? Get all big and shredded, right? They're putting energy in and building up. Okay? You don't find like that skinny little wiry guy being like, yeah, dude, I've been doing steroids for 6 years. Okay, then you're doing them wrong, right? So catabolism then is breaking those bonds down. We're not building them up. Is this idea is really important, you guys. I don't want you to miss this. So once again, endergonic, putting energy into the thing building chemical bonds. Exergonic reactions, I'm getting the energy out of the thing, of those little molecules. I'm doing catabolism. I'm breaking things down. Okay. Mm-hmm. Yep, this is energy in. Energy is going into these reactions. This is energy coming out or releasing energy. Anabolism is building up. Catabolism is breaking down. Since the first time I learned this, you guys, I can't see this word and not picture exploding a cat. Sorry. If you're a cat person, I apologize. But every time I say catabolism, I see this little cat going like, because it's taking that thing and it's breaking it apart. Okay? I will not show you YouTube videos of cats exploding because I can't show you any video. But what? Yeah, that one would work, right? And then I'd get fired for. Anyway, we okay on this idea? Because this one's pretty important. Some of these other ones, maybe not so much, but some of these concepts will come up over and over and over again. Okay, entropy, another idea that's kind of important. The idea behind entropy is that without energy, this is really scientific, you guys, stuff goes to crap. You write that down, put it on your wall, right? But it makes sense. Think about your bedroom if you don't invest a little bit of energy into it. Over a period of a couple days, weeks, or months, what's going to happen? Are you going to walk in one day and be like, whoa, my room's clean? No, you're going to walk in one day and be like, I smell something dead somewhere. I probably better clean this place, right? Because unless you're committing some energy to it, things tend to become more disorganized. Okay, I love this picture. I don't know who drew it and why, but they're like, if some guy wore a weird sweater and just threw bricks into the air, what's going to happen to those bricks? Are they going to line up all perfect and pretty? No, that just doesn't make sense. They're going to end up in a big old crappy pile. Okay, so that's the idea. Entropy just means things go from organized to unorganized, unless we're doing something with them. If you started off with molecules that were nicely packed and organized, and you just let them sit over time, they're going to become disorganized. If I took this table with its nicely packaged molecules and I left it for 200 years, is it going to look more organized after 200 years? No, it's going to look like a pile of crap, right? Because without energy, things just go to crap. Okay. Diffusion is a very important term. We're going to spend lots of time talking about diffusion in like 3 modules. But it's a kind of entropy. It's like when I have stuff that's organized and I just leave it alone and let it go to unorganized. Okay, like if I put a lump of sugar in a beaker of water. It's going to start all nice, packed together and organized. And over time, those molecules are just going to start to move about and become less organized. Okay, the story I always share, and it's like my favorite story. So going back to growing up in maybe a neighborhood that wasn't, I had no idea that it wasn't great, but maybe it wasn't. So after school, there was always an ice cream man that would park his truck right around the corner. So far enough away from the school that I guess he couldn't get in trouble. But this ice cream man was a little bit shifty. And I didn't find out about it until like 6th grade, and I was so bummed. But apparently he had like a secret menu of stuff. And he'd only show it to you if you like asked for it. So kids would go up and they'd get their like ice cream and their candy cigarettes like crazy. But you'd be like, hey, I want to see your secret stuff. And he'd be like, I don't know what you're talking about. And you'd like put your money on the counter and be like, I know. So he had this board that had like all the little popsicle flavors on it. He would flip it around and have like Chinese stars and nunchucks and smoke bombs and like all sorts of sketchy crap, right? But people would buy smoke or stink bombs from him all the time. So these little glass vials, they're only about that big. But you'd walk into a classroom, you'd break the thing and throw it in the garbage. And then you'd sit down, all cute, like, hey, let's begin class. Well, what would happen to that tiny vial of stink after a period of about 10 or 15 minutes? Those tightly packaged and organized stink molecules start to do what? They start to spread throughout the room, okay? They start to diffuse from where they were in high concentration to where they weren't so high in concentration. So I swear it was like once a week you would walk outside of my school, because my school didn't have halls, it was in Phoenix, and you would see like entire classes like out on the field having class because someone had stink bombed the room. It's kind of funny, right? They smell terrible. But the idea is that's diffusion. It's a kind of entropy. You put those organized molecules into an area and then open them up, and they over time just start to diffuse out into the space. Okay, we'll come back to diffusion, talk quite a bit about it. Really, by definition, it's moving from, and you guys have heard this before, what? High concentration? Yeah. To low concentration. Is that okay? Okay, questions about our random facts here today? Still okay? Okay, specific heat. This is another kind of weird idea, and we're not going to get way too in-depth on this, but what we're talking about is what happens with different substances as we try to heat them up or we try to cool them down. Certain things heat easier than others. Other things take a little bit more time. So when we're talking about that property, we call it specific heat. Okay, and it's essentially what does it take, how much heat does it take, if I have a gram of this stuff and I want to raise it by 1 degree. Okay, so I could take 1 gram of water, hit it with my torch, and measure it. Once it goes up 1 degree, I'm like, yay, that's how much energy it took. And I can take a penny and do the same thing with a penny. And I can take a finger and do the same thing with a finger. And I'm getting a specific heat for different things. Okay, so some stuff, we call them conductors. They take the heat and they kind of hold on to it. They like it. Okay? So these guys are going to have lower specific heats. It doesn't take a whole lot of heat to warm these guys up. Okay, you could take, if you could find a copper penny, you could hit it with some heat, and 20 seconds later, put it in your hand, it's still going to feel warm because it's kind of holding that heat. It's storing it. Okay, so we call these guys conductors. I remember making tinfoil cookers. Remember doing this like in 7th or 8th grade? You're learning how like light reflects, and if you haven't made a foil cooker, make one this week, and they're kind of fun. But we lined ours with pennies, going back to the nerd idea. So all of this heat that came in got stored by the pennies. So my little team of dorky 7th grade scientists, we melted the teacher's thermometer. We were like, what now? Thinking we were cool. Then we got beat up in PE later that day. But the idea is that we had an idea or an understanding that some things hold on to that heat and increase the heat. Okay. Other things, they don't heat up quite so easy. And so instead of absorbing the heat themselves, they kind of push it away. And so for that reason, we say these guys are better insulators. Okay, so after I moved up to Utah, I got involved in like the youth group at church, so I was a scout leader. And they said, we're doing Kwanzas. Anyone know what a Kwanzaa is? Growing up in Phoenix, you never have the opportunity to learn what a Kwanzaa is. It's a damn snow cave. Okay, so we were going to go build snow caves. I had no idea that you would build these giant mounds of snow, then you hollow them out, and then you sleep inside. When you have a home with a bed and heat, you go out into the forest and sleep in a snow cave. This is something people do. Okay, so I'm like 26 years old, never done this thing before. I thought I was going to freeze to death. Okay, spoiler alert, I did not. Did not lose any of my fingers to frostbite, because it turns out that ice is an okay insulator. Just okay. Don't write in there that it's a great insulator. We weren't warm. Okay, we were sleeping in a damn snow cave. But it did trap some of the heat that we were producing. In fact, we had a leader that showed up so we did our little cave thing, hollowed them out. We had one for the boys, one for the leaders. The boys' cave in the morning at the entrance, because you do the entrance below and you kind of climb up into it, was perfectly yellow. You know why? Because none of them wanted to leave the cave to go pee. So they just peed from, it was disgusting. So to get out of the cave, they all had to slide anyway. But we had a leader that showed up 2 hours after we had built these things. And we were like, Gary, we don't really have room for you in our snow cave. He's like, that's okay. He dug a ditch in the snow and just like laid in it and then like pulled the snow over the top of his sleeping bag. Literally, I was like, well, Gary's going to die tonight. We're going to wake up and have like frozen scout leader and have to like call his wife. He also did not die because the ice kind of insulated him a little bit, right? How many times have I been this close to killing people on scout trips, yet I still get called to do it over and over again? But that's the idea. So he had taken advantage of the fact that being inside of this little trench, even with some snow on top of him, that snow was kind of trapping his heat, which would have been better than just laying on top of the snow being exposed to the cold air. So he was smarter than I was in that moment. Idea making sense. Different substances conduct or hang on to the heat. Other things insulate or kind of push it away from themselves. And we use specific heat to measure that. Okay, these specific heat, these are measured in calories. Okay, but it's a little bit different than these calories. These are food calories, and this is what you've heard of before. So we're talking about food calories. What we're talking about is the ability for that food molecule to be broken down into energy molecules. Okay, so we get food calories, and I love this chart because who in the world came up with this? They're like, hey, if you eat 2 slices of cheese pizza, that's about 800 calories. That part I'm cool with. I'm like, yeah, great, we can find calories for everything. And they're like, just if you want a point of reference, that's like 86 to 92 minutes of playing basketball. How would you ever know this, right? What if you're like playing really, really hard or just shoot? You know what? If you want to, like your friend calls you and they're like, hey, we're going to go to the park and play Frisbee. And you're like, well, for how long? And they're like, 25 to 30 minutes. You're like, okay, hold on. I need to eat a breakfast pastry. Right? Or what's the other one? There's one on here that's super funny. Windsurfing. You know? Let's go windsurfing for half an hour. Hold on, I need a banana. But what we're trying to say is we take food and we convert it to energy, and then we can use that energy for what we generically call work or doing something. Okay, whether it's canoeing. I love slow jogging. Not just jogging, not walking. Slow jogging. You better have some strawberry yogurt. But you get the point, right? We're trying to demonstrate the idea behind food calories. Any questions about this? We will not ask you like, hey, you plan to go mountain climbing with your friends. Which of the following? Understand, food has calories. Those determine the energy we can get from it.
So on this slide before, with the specific heat, you need to know all of those.
Hell no.
Okay.
Sorry. I had a goal to not swear, and I'm sorry. Send me a message, say, please stop swearing, and I'll do my best. But yeah, there are some things that are just so detailed. No. The concept of what is a heat calorie or specific heat, it's a measurement of how well something hangs on to heat or how well it does not. Kind of puts it up. Yeah, great question. More likely the question you're going to get is something like, which of the following would be a good conductor of heat? Water, ice, or gold? And then you're like, oh wait, gold was my better heat conductor. Or we would say something like, lead has a specific heat of 0.03. Ethyl alcohol has a specific heat of 0.5. Which one's going to be the better insulator? This guy.
What's the definition again? It's a measurement of...
So the actual definition of specific heat is how much heat does it take to raise 1 gram of a substance by 1 degree centigrade. So that's what the heat calorie is. Food calorie is just that we can measure the amount of energy producing molecules that are present in a particular food. Just how much energy we can get out of the food, and we measure it in calories. I do plan to go to the gym later today for probably about an hour, so I'm going to make sure I have 3 chicken wings for lunch, if anyone's wondering. Okay, a couple more little bits that we'll throw out today until we're to that stopping point and you guys are so bored you want to die. Chemical symbols for some of these guys. Some of them just make sense, like oxygen. Well, it starts with the O, so let's go with O. Okay, aluminum, it starts with the Al, so we'll go with Al. Boron, B for boron, boring, right? Carbon C. Those guys should be pretty easy. We do want you to have a handle on them. What I would say pay attention to are the ones that are a little bit weird, like copper. Comes from the Latin cuprium, which is copper. So it has a different chemical symbol. Okay, potassium, like we said, has a K. Sodium is Na. Iron is Fe. Tin is Sn. Those are the ones that you're going to see that are abnormal or weird, but they pop up in like human chemistry. Okay, the rest of them, we're not going to ask you like the weird, like, you know, atomic number 700 or 112, some weird radioactive thing. Don't stress about those guys. But these guys you should be at least able to recognize. Yeah, Fe is the chemical symbol for which element? Copper, iron, oxygen, plutonium. You're like, I remember that guy's iron. Yeah, really pretty simple. We okay on that? Unfortunately, there is just some straight-up memorization type stuff here. Okay, I just want to introduce the periodic table, and then I promise we'll call it a day. I remember seeing this for the first time and having my chemistry teacher get like all excited, like weird, like childhood Christmas excited, like the periodic table. To me, it's cool, but my shower curtain at home isn't the periodic table, right? Like on the Big Bang Theory. I don't love it that much. But it is kind of a cool way to organize these elements because it puts them in places where you can get some information about the element and what it's going to do. Okay, so the organization of the periodic table is really pretty cool. Main thing that we see on it is we can draw a line here, and we say everything over here is a metal, and everything over here is a non-metal. Okay, that's what we mean by this part here. So elements on the left side of the table are metals, elements on the right side are non-metals. Okay, that's one big separation that we have here. Okay, is metals and non-metals. On the far right side, these guys here, we call them the noble gases. I want you to think already off the bat, noble means snotty. Okay, and we'll explain what that means down the road. But if someone's very noble, think of them as being snotty, okay? And that'll help us out a little bit down the road. Okay, but most of these guys that we would see in solid pressure draw the line there, because aluminum's definitely a metal. But these guys over here, they're going to have similar properties versus these guys here that don't react quite the same, don't interact with other things quite the same. In addition to that division, we have columns. And all of the guys in these columns, and you can see the column names here, they're going to have similar properties too. So nitrogen is going to do similar things as phosphorus, as arsenic, as antimony. Okay, we'll go through these and we'll kind of talk about what do we mean by these similar properties. But it's kind of important to see there's some organization. The other thing that's going to be important is that you see we've got these numbers here. And these numbers are going to give us a lot of information as well. And so we call that the atomic number. But we can use those atomic numbers to kind of figure out how that element is comprised or what it's made of. Okay? So there we go, metals, non-metals. We've talked about this. Let's zip through it, and then we'll call it good. Because this is what we introduced all of this with. So matter, stuff in the world, is made up of these tiny particles. Okay, we have